The Science of Planetary Protection, Preserving Celestial Environments. Title: The Science of Planetary Protection, Preserving Celestial Environments. Introduction. As humanity ventures deeper into space exploration, the science of planetary protection has become a critical aspect of ensuring the preservation of celestial environments. The delicate ecosystems on other planets and moons hold valuable scientific insights and may even harbor signs of extraterrestrial life. With this in mind, rigorous measures are put in place to prevent any contamination from Earth that could jeopardize these pristine environments. In this article, we will delve into the science of planetary protection and the measures taken to safeguard our celestial neighbors. Understanding planetary protection. Planetary protection refers to the set of protocols and policies aimed at preventing biological contamination, both forward and backward, between celestial bodies and Earth. These measures are necessary to preserve the integrity of potential extraterrestrial environments and also to protect our planet from potential hazards present in alien environments. The main goal is to avoid false positives or negatives in our search for life beyond Earth. Forward contamination. Forward contamination involves the inadvertent transfer of Earth microbes and organic compounds to other celestial bodies. The primary concern is that if life indeed exists beyond Earth, it could be attributed to contamination rather than naturally occurring. Precautionary measures, such as stringent cleanliness protocols, are implemented to reduce the likelihood of contaminating other celestial bodies with spacecraft, landers, and rovers sent from Earth. Spacecraft assembly facilities are designed to limit the microbial load on outgoing missions. Teams of engineers and scientists ensure that every component of a spacecraft is thoroughly cleaned and sterilized before launch. Additionally, cleanroom facilities maintain strict air quality standards to minimize the introduction of microorganisms during final assembly. Backward contamination. Backward contamination is the potential contamination of Earth with alien organisms or organic compounds brought back from other celestial bodies. While this scenario is more hypothetical at present, it is essential to consider the risks. The Apollo lunar missions underwent rigorous decontamination protocols, including quarantine measures, upon returning from the Moon. Special attention is given to the selection of landing sites and sample collection techniques to avoid areas where extraterrestrial life may exist. The proper handling and containment of samples upon their return to Earth is of utmost importance. Isolation facilities, like those used for handling highly infectious diseases, would likely be employed to ensure proper containment and analysis without compromising terrestrial environments. Planetary protection categories. To address the diverse missions and associated risks, the international space community has established several categories within the planetary protection framework. These categories help categorize missions based on their destinations and the potential for biological contamination. Category I pertains to missions that do not involve any direct contact with celestial bodies and have no significant chance of contaminating them. These include missions such as flybys or those involving the study of the interstellar medium. Category 2 comprises missions to celestial bodies where the potential for introducing Earth microbes needs to be carefully considered. Most robotic explorations fall into this category and require sterilization measures to reduce the likelihood of contamination. Finally, Category 3 consists of missions aimed specifically at determining the presence of extant life or its remnants. This category encompasses ambitious sample return missions where the highest level of protection is implemented to prevent backward contamination. The role of the Outer Space Treaty. International collaboration is a critical aspect when it comes to planetary protection. The Outer Space Treaty, signed by numerous countries, outlines general principles for peaceful exploration and non-interference. It emphasizes the importance of avoiding harmful contamination, especially regarding celestial bodies that might contain life or the potential for life. Agencies such as NASA, ESA, and Roscosmos work together to draft unified planetary protection policies and guidelines. These are critical in establishing a comprehensive framework to ensure consistency in mission planning and execution. The future of planetary protection. With increased interest in crewed missions to Mars and the potential for sample return missions from other celestial bodies, the field of planetary protection is evolving rapidly. Scientists and engineers are continually developing new technologies and protocols to enhance our understanding of extraterrestrial environments without compromising their integrity. Future missions will require precise and advanced analytical techniques to identify potential indicators of life without risking contamination. By using instruments capable of detecting even trace amounts of organic compounds, we can minimize the need for direct contact with delicate environments, ensuring the preservation of alien habitats. Planetary protection is a critical aspect of space exploration, ensuring the preservation of celestial environments and potentially protecting Earth from any hazards present in alien environments. Measures are put in place to prevent forward contamination, which involves the unintentional transfer of Earth microbes and organic compounds to other celestial bodies. This contamination could potentially be mistaken as extraterrestrial life. To minimize this risk, spacecraft assembly facilities follow stringent cleanliness protocols and maintain strict air quality standards. Another concern is backward contamination, which involves the potential contamination of Earth with alien organisms or organic compounds brought back from other celestial bodies. Although this scenario is currently more hypothetical, it is essential to consider the risks it poses. Past missions, such as the Apollo lunar missions, implemented rigorous decontamination protocols, including quarantine measures, upon returning from the Moon. If future missions involve sample return missions from Mars or the moons of Saturn and Jupiter, even more stringent containment measures would likely be necessary. To address the diverse missions and associated risks, the international space community has established categories within the planetary protection framework. Category A includes missions that do not involve direct contact with celestial bodies and have no significant chance of contaminating them. Category 2 comprises missions to celestial bodies where the potential for introducing Earth microbes needs to be carefully considered and requires sterilization measures. Lastly, Category 3 consists of missions aimed at determining the presence of extant life, requiring the highest level of protection against backward contamination. International collaboration is crucial in the field of planetary protection. The Outer Space Treaty outlines general principles for peaceful exploration and non-interference, emphasizing the importance of avoiding harmful contamination. Agencies like NASA, ESA, and Roscosmos work together to establish unified planetary protection policies and guidelines, ensuring consistency in mission planning and execution.